Hi, and welcome to the Kubernetes podcast from Google. I'm your host, Abdel Seguiwar.
And I'm Caslin Fields.
In this episode, we chat with Fabian Kammel. Fabian is a security architect at ControlPlane, working on confidential computing for the cloud-native ecosystem. Stay tuned to listen to our conversation about confidential computing, standards, open projects, and what's going on in this space.
But first, let's get to the news.
Istio have been recognized as the best open source software of 2023 by the InfoWorld BOSE Award. Congratulations to the Istio team.
On November 7th, Google Cloud announced the general availability of GKE Enterprise, a premium new edition of Google Kubernetes Engine, which integrates enterprise-grade tools with a unified console experience. Notable features of GKE Enterprise include fleet team management, enabling platform engineers to easily group similar workloads into dedicated clusters, apply custom configurations and policy guardrails per fleet, isolate sensitive workloads, and delegate cluster management to other specific teams. Teams can run and manage their workloads as well as view logs, resource utilization, error rates, and other metrics, all scoped to their own set of clusters and namespaces.
On October 31st, the Google Kubernetes Engine team also announced the general availability of the multi-cluster gateway controller for GKE, which natively supports the deployment of a unified application load balancer for a fleet of GKE clusters using the Kubernetes Gateway API. With the multi-cluster gateway controller, GKE shops can implement sophisticated patterns such as blue-green deployments or geo-distributed applications, while keeping their most valuable assets protected with advanced security capabilities integrated with Google Cloud's application load balancer.
GitHub's major conference, GitHub Universe 2023, took place November 8th and 9th in San Francisco, California. Announcements generally followed the industry trend of AI all the things, with a major focus on GitHub Copilot. GitHub announced general availability of GitHub Copilot Chat and previews of the new GitHub Copilot Enterprise offering, new AI-powered security features, and the GitHub Copilot Partner Program.
Microsoft flagship conference, Microsoft Ignite, took place in Seattle, November 14 to 17. Announcement from the Azure Kubernetes Service team included Fleet Manager general availability, artifact streaming for Linux in preview, app routing general availability, confidential containers in preview, cost analysis add-on and Azure cost management integration in preview, Microsoft Copilot for Azure, and AI toolchain operator for hosting LLM models on AKS.
The CNCF announced the establishment of Cloud Native Community Japan, a Japanese chapter of the CNCF. The new organization will serve as a hub for the Cloud Native Computing Foundation and Japanese community to promote cloud native and open source in the region.
Vitess announced the general availability of Vitess 18. The new version brings new enhancements to improve usability, performance, and MySQL compatibility. Vitess is a CNCF graduated project and an open source tool that can be used to run horizontally scalable MySQL and Percona server databases in cloud native environments.
And that's the news.
Hi everyone. Today we're talking to Fabian Kammel. Fabian is a security architect at ControlPlane. That's ControlPlane, similar to Kubernetes ControlPlane, but one word with a capital P. Fabian works on securing cloud native architectures, mostly focusing on implementing hardware-based security. Some of the notable projects Fabian have worked on are things like PKI on road vehicles, which I'm very curious to understand what that actually means. Always-encrypted Kubernetes distributions, and very recently working on a SPIFFE-based machine identities via hardware attestation. Welcome to the show, Fabian.
Thanks for having me. I'm super honored to be here.
Thank you for accepting my invitation. It was kind of very last minute, so thanks for being here. We wanted to chat with you because there was a very interesting article about confidential computing that you co-authored on the Kubernetes documentation. So let's start with a very basic question. What is confidential computing?
Right. So confidential computing you see a lot more of, I feel, in the recent months. But this is basically a concept or a thing we did forever, right? So we had specialized hardware to have hardware protected environments to shield basically super sensitive computations we were doing, right? So think about like your credit cards or like the SIM card in your phone or maybe even stuff like TPMs or HSMs.
Yeah.
So every time we do a trusted computation in an untrusted environment, and this is also why we generally refer to them as like trusted execution environments. So confidential computing basically takes this concept and enables more use cases. It makes it available in like just consumer or like server hardware. So you can run your web server on it in a secure way. You're not going to run your web server on a smart card, right?
Yeah, of course.
So as well as it also provides remote attestation. And this is a super crucial feature where you can remotely verify that the environment you're running in is genuine, right? So most of the time today, you don't have physical access to the machine you're running on, not only in the cloud, but also like data centers are usually managed by some third-party provider.
Yeah, or maybe you even buy a laptop and you don't know where it's coming from, right? So
also, yes.
I think the idea of computational computing is not new because you mentioned TPMs, and we're going to talk a little bit more about that.
Yeah.
But before we go there, the article mentioned something called the Confidential Computing Consortium, which is a sister organization to the Linux Foundation, right?
That's correct. So
what is that?
Yeah, it's a group in the Linux Foundation ecosystem, and they basically try to work on this in a vendor-neutral way, right? They have a white paper, which is super excellent to read if you're new to the topic. It will introduce you to a lot of the concepts and the topics, and also how to make use of them and how to securely run this stuff. But they also help to like facilitate and like grow open source projects in that space. So for example, we have the Confidential Container Project. I think we will talk about this a bit later in the show.
Just because I like the name, it's Coco.
It's awesome.
Yeah. All right. So you mentioned quite a lot of things, and we'll try to unpack as much of these things as possible.
Right.
I did skim through the white paper. It does a very good job at explaining some basic concepts. We'll try to explain some of them today, but if we don't get to explore all of them, I really highly recommend people to write the white paper. So let's try with the TEE, Trusted Execution Environment. What is that?
So TE is very loosely defined term, right? It's just any hardware protected environment where any outside observer is not able to see the data you're basically working with or working on, right? They cannot watch what you're doing and they cannot manipulate what you're doing. So everyone outside of the TEE doesn't know about the data you have. So the TEE is very differently defined in the different contexts. So we have, for example, Intel SGX, which is one implementation of a TEE, which is process-based. So in the same operating system, you have lots of different processes doing work, and you can request the Intel chip to create a new process that is memory encrypted from the rest of the system. Mm-hmm. You have other technology out there which defines the TEE a bit broader, like with AMD SMP, for example, you get a whole confidential virtual machine where the full virtual machine is shielded from other virtual machines on the same host CPU.
And is this supposed to be like transparent to the application? Is the application supposed to not know it's running inside the TEE?
Yes, exactly. So Intel SGX is process-based, so you don't have access to the operating system, and you usually need to have an SDK and port your application to that SDK to make it work inside Intel SGX. But if you run into in a confidential virtual machine context, it's really transparent. Like you just lift and shift your application, you take your database, you take your web server, whatever, and you run it in this confidential virtual machine.
Yeah, and I guess that's essentially what most cloud providers are doing today, is providing CVMs, right? Cloud virtual machines.
Exactly.
Well, confidential virtual machines, sorry.
The popularity of the CVMs is a lot bigger because they're like easier to use.
Yeah.
But they also have like different security assumptions, right? You need to trust all the processes running in the same CVM with you.
Yes, the management software, whatever that management software is, I guess, right?
Yeah.
Okay, so before we move on, we'll leave some time to like deep into the CVMs. The article mentions enclaves. So what are enclaves and how different are they from TEEs?
Enclaves are basically just one implementation of a TEE. Mm-hmm. You most often heard the term enclave when it comes to Intel SGX. So Intel SGX creates this process, or this isolated process, which is like memory encrypted. And this memory encrypted process or environment is called an enclave.
Okay.
So you can, as a normal process on an operating system, you can reach out to the Intel CPU and say like, hey, I need one of those enclaves to do like sensitive computation. You get this process, which is memory encrypted, and you can load in both code and data. You can choose to load it when it's encrypted and only have it decrypted inside this enclave, and then run your sensitive computations in there.
And then commit it back to memory and then potentially persistent back to disk.
Right. You can like encrypt it again before you send it out of the enclave and then store it securely somewhere.
Okay. So I'm thinking here with my very, very like old Linux hat, sysadmin. What about swap memory? Because that's technically disk-based, right?
Yeah.
So would that be considered in an enclave or in a TEE memory as well?
I don't know about the specifics. Like there are certain ways on how to like flag certain memory pages of being encrypted and not being encrypted and so on. So you really have to look into the details on like which parts of your application are secured.
I see. Okay. I was just thinking about it because we were doing an episode about Kubernetes 1.28, and Kubernetes notoriously was actually not very fan of having swap on nodes.
Yeah.
But they just enabled this very recently. So I was very happy when I saw that. I was like, yes, finally, Linux coming back. but yeah, anyway, I think, yeah, as you said, I think it depends on the implementation. So, okay, TEs are sort of like a generic, loosely defined term. Enclaves is one implementation by Intel.
Yes.
But then you also mentioned in the article, but also in the conversation, HSMs and TPMs. So HSM stands for Hardware Security Modules, and TPMs are Trusted
Platform Modules.
Yes. So how different are these new, like modern patterns from it? Because HSMs and TPMs existed for a while, right?
Yeah, for quite a while actually. And like TPMs are just commonplace. Like every main board that is built into like a server, a desktop, a laptop, whatever, it has a TPM. And these things are super cheap, like a few cents maybe, but they're also super limited in their capabilities, right? They only have kilobytes of memory. They can store a few cryptographic keys, which usually are used to like give your machine an identity. And then you have a few cryptographic operations they can carry out. Maybe do a signature or like do an encryption operation, stuff like that, or generate a new key. So again, these are not programmable. You can't run your web server in a TPM.
Yeah.
On the other hand side, we have HSMs, and these are hardware security modules. These are expensive, like 10K and up.
Yeah.
But these come with quite powerful features, and I used this in the past when I did PKIs for automotive, and you store like the root of trust or your root certificate, like the very crown jewels of your cryptographic keys in these HSMs, because they are really worth it to spend this much money to have them secure. So HSMs have like physical tamper protection, right? If someone tries to like break open the server and like steal the disk or steal the RAM or whatever to read out the keys, the HSM will know, shut down, null all the memory so no one can steal your data.
Oh, interesting.
But again, this is way too expensive to run your average workload and make it more secure. So what these new primitives do is basically allow you to run arbitrary code, get a good performance on a standard server CPU price.
I see. There are a lot to unpack actually about HSMs, which I think that people who are using HSMs in the cloud, they just think about them, okay, well, I store my keys in an HSM, and then I use the HSM through typically Cloud API to do my encryption, decryption, signature operations, right? When you are using a cloud-based HSM or even a physical HSM, I guess that the cryptographic operations happened in the HSM itself, right?
Exactly.
So you would send your encrypted data to the HSM, that the decryption operation, whatever operation happens inside the HSM itself.
Yes.
So there is a certain level of protection, and then you will receive the unencrypted data.
Yeah, this is one use case, right? You can think about like having like a certificate signing request, and you send this to some PKI provider, and they will have like some sort of HSM in the backend, and the HSM will do like the cryptographic operation to like issue the new certificate for you.
Yeah.
Other cloud providers use this, for example, for key derivation. So if you do like disk encryption and you want to encrypt all of your disks, you have like one master key in the HSMs, and you just derive new keys from that master key to decrypt or encrypt all the disks you want to attach.
Yeah, you do like it's called dual envelope encryption or something like that, or envelope encryption. Yeah. That's also very common. Okay, that's actually quite interesting. I remember watching the videos of the, I don't know if you know this, but like the root certificates for the top level domains, they have like a ceremony to be able to generate them. And they do usually use HSMs. They are just smaller form factor. They're just like an USB stick or something like that, right?
Yes, exactly. And you can also buy them if like a security geek. They're like these USB form factor HSMs. If you want to store like your PGP keys or whatever, you can get them from YubiKey or like other popular vendors.
Yeah. That's actually, I was about to mention, like YubiKey are technically HSMs, right?
Yeah.
So, yeah, cool. So then moving forward, I guess, because I think in terms of probably if we want to talk about this from a chronological point of view, HSM, TPMs, then TEs is kind of somehow modern as a concept, and then cloud virtual machines or confidential virtual machines. It's confusing. I think that CVM should be called CCVMs, Cloud Confidential Virtual Machines.
But they are not native to the cloud, right? So you can just get like the AMD or Intel chip or whatever enables it, just run it in your local data center or like at home if you have the funds to do so.
Sure. Okay, yeah, that's probably because I work in cloud. Okay, so confidential virtual machines, what are those? Like, what do we mean when we say a CVM?
A classical virtual machine, if you think of the stack of all the components that have to come together to create your virtual machine, right? So you have the CPU that runs some sort of firmware which controls like the microcode. You have like the host operating system that runs the hypervisor. And then you ask the hypervisor to create my virtual machine, which has like, again, like some sort of firmware emulated, maybe bootloader, kernel. And there's all this stuff going in. And you need to trust all these different components to not be malicious and like do some malicious stuff with the virtual machine you want to create. So confidential virtual machines basically allow you to then request the CPU directly to create this memory encrypted virtual machine. Mm-hmm. And this basically isolates you from the rest of the system. It isolates you even from the hypervisor. The hypervisor is no longer able to look into your virtual machine because it's memory encrypted, and the hypervisor doesn't have access to either look into the memory pages or like get the decryption key.
Mm-hmm. So in a context of a typical hypervisor, where the memory that the virtual machine gets is mapped out of the physical memory of the host, right?
Yes.
And then it's remapped through the hypervisor to look like one big memory page or multiple memory pages or whatever, right? So would the encryption happen at the hypervisor level, or is it at the virtual machine? I don't know if you're getting what I'm trying to get at with my question.
Yes, definitely. So where does the encryption basically happen? And It happens in the CPU. So if you look at the AMD example, so the AMD technology for this is SEV-SNP. SNP stands for Secure Nested Paging. So this is actually exactly what you mentioned. So the CPU will memory encrypt the memory pages.
Yes.
So the hypervisor doesn't have access to them, and only the virtual machine will get a clear view of the memory pages.
Okay. And in this case, where would typically the encryption keys would be stored?
So they reside in the CPU and like secure registers, and they can't be retrieved, right? The CPU just uses them for encryption operations to keep your memory pages safe and like shielded from the rest of the system, but they never leave the CPU itself.
But then how would the CPU pass those encryption keys to the virtual machine? Because the virtual machine or the guest OS will have to decrypt or...
That's aware of the context, right? It can make these memory pages available in plain to your virtual machine, but not to the host or like the hypervisor or other guests running on the same system.
I see. Okay. So that's a way to keep the memory pages encrypted on the physical host across the guests, essentially, right?
Yes.
Interesting. Okay. Yeah, I think that the nested virtualization makes it a little bit complicated to understand where the encryption happens exactly. So
yeah, it also required a lot of code changes in a lot of places. So the hypervisor and the client and everyone needs to be aware of that new paradigm. So it took quite a while to actually get the full support for this new type of VMs. Mm-hmm. But since this year, you can actually use them in most of the cloud providers.
And I assume also most of the common upstream hypervisor technologies like VMware and whatever.
Yeah.
Okay, cool. Okay, so I think that clarifies quite a bit what a confidential virtual machine is. And I think in the context of a cloud virtual machine or a cloud confidential virtual machine, that essentially means that as a customer, I know that my virtual machine, which sits typically on a multi-tenant environment, is shielded from the other tenants, right?
Exactly. So it's shielded from a lot of potentially malicious parties, right? We saw attacks in the past of malicious other virtual machines that try to listen in on like what is going on the CPU, or even attack like the hypervisor to get access to the other VMs. You shield it from the hypervisor itself, which would be like the cloud provider is no longer able to look into your virtual machine. Not sure how often they do it, but they definitely have the capability to do it.
Yeah.
And you also shield it from like attackers that are running in the network of the cloud provider, for example.
Yeah, I was about to ask that as a follow-up question. So what about the network part, right? Because eventually as a virtual machine, you will have to send some packets through the network, which in a cloud environment, it's typically a shared environment, right?
Yes, exactly. And this is why it's super critical to have all the encryption pieces in place, right? We often talk about this triad of encryption you want to have in your application. So you have the encryption at rest. So like you want to have disk encryption. So if something is written to the disk and someone steals the disk, they cannot read out the information. You also want to have the encryption in transit. This is why you want to use like TLS, or even better like mutual TLS if you know both parties of the conversation. What confidential computing is now giving you to also have encryption in use. When you use the data, when you have it in memory, people outside of this TEE, so other VMs or the hypervisor, are not able to read the data you're handling. So you can really put very sensitive data in the cloud and be sure no one can read those.
Yeah. So we'll dive a little bit more into the CIA triads. But before that, in the article, as I was reading through it, there was this mention of something called TCB, Trusted Computing Base. What is that?
So this is basically a fancy term to mean every component that is critical to the security of your whole system, right? So we looked at the stack, every software component that needs to come together to produce this virtual machine you want to run. So if we only attack like one piece of the puzzle, if we attack the hypervisor, we can probably break the security of your virtual machine. If we attack the firmware of the CPU, probably attack your virtual machine and so on. Like it's the bootloader, it's the kernel, it's all the different components that are going on. Mm-hmm. And confidential computing is helping us twofold, right? With the memory encryption, which is an important part to get rid of the hypervisor, but also the parts that are running in the same TEE. So our bootloader or like our operating system, we have this feature called remote attestation. Mm-hmm. And this is quite cool. This is like measured boot, but on steroids.
Okay.
So you're measuring the memory pages as your VM boots up, and you can store like a hash of all the memory pages involved in the boot process of your virtual machine, mm-hmm. and store them in special registers. And these registers are not controlled directly. You feed in some data, they get hashed and appended to whatever is there. So like no one can control the value directly, but you can feed in measurements or like information about the state of the system. Mm-hmm. And you can then request an attestation report, which contains all of these measurements from like the outside of the virtual machine. So before you put your sensitive data into this VM or this CVM, you can check, is it actually running the software I'm expecting it to run? And only if it's good and then no one like tampered with my bootloader or my operating system, I will explicitly trust that CVM to be good, and then I can authorize it to run with my sensitive data.
I see. So, okay, there is a lot to unpack there. When you were talking about during boot time, hashing the memory, is that a way to ensure that the bootloader have not tampered with the virtual machine in such a way that it makes it read data from a memory page where an attacker would put some random stuff, right? Is that the case?
Yes, exactly. So you could imagine like someone attacks your bootloader to like send passwords to like some remote server or whatever, like put in a backdoor to SSH into your system. But this is a change to the code, to the bootloader itself, right? And if we measure the bootloader before it's being used in our boot chain, and we make this information available, we can actually compare, like, is this the bootloader we expected to run? And if it's not, we would just not make our sensitive data available to the CVM.
Okay, that's actually a very clever way of doing it. Like you have a base to know, I guess that's probably where TCB comes from. You have a base to know how the bootloader looks like at boot. And then when you run it in a non-trusted environment, in a cloud environment, then you have a report of how this actual bootloader is behaving, right?
Yes.
Interesting. Okay, interesting. Yeah, because as you were talking, I was thinking like, yeah, that's one of the most common attack vectors, which is expand the memory, right? Make the bootloader read something from somewhere where you would have a backdoor or you would have an SSH key or something like that, right?
Yes, exactly. And like you can use this concept of the remote attestation for a lot of different purposes, right? So maybe you want to have like an audit log of all the systems you fed your software to. So like you can even store these memory measurements for future audits.
Yes.
Or you can use them for like explicitly authorizing or not authorizing a system to access your data.
Yeah, so this is in the context of something like a regulated industry or something, in case you need...
Yes, exactly.
Yeah, in case you need access to that information. Okay, so that's partially what remote attestation does, if I get it correctly, right? Mm-hmm. Is there anything else that... I mean, for me, the first time I heard about remote attestation was in the context of signing an image, for example, before it's deployed to a target system. By image, I mean a container image, right? Before it's deployed to a Kubernetes cluster. So you have a Kubernetes cluster. The Kubernetes cluster has a bunch of keys or has basically a remote CA, right?
Yeah.
And then you would sign your images with certificates coming from that CA. You would deploy them to Kubernetes. Kubernetes will reach out to the CA to verify, have these images been attested, right?
Yeah.
Which I guess is the same concept.
Exactly. It's a similar concept. So Also, the remote attestation report you get from the confidential VM, this is signed usually with X509 certificate chain.
Yeah.
And this is the same thing we also do for software binaries, for like container images. So we have a digest we expect to run, and we have it signed so we can cryptographically verify it and tie it back to some root of trust. For like CVMs, this would be like AMD or the chip vendor. For software or container image, it's usually the software engineer or like the release engineer who produced the binary.
Yeah. So way to cryptographically verify the origin of a certain piece of artifact, essentially.
Yes.
All right, so cool. We talked very briefly about the CIA triad, which I'll briefly mention it. CIA triad in security means confidentiality, integrity, availability, right? Which are sort of the three main things that you need to ensure exist to say that the system is secure. I'm dumbing this out quite a lot. So can you give us a little bit more, can you shed light on CIA and how it plays out in the context of TEs?
Yeah, definitely. So as you mentioned, like CIA, this acronym or like these three pieces is like usually a good frame or like framework to start to think about the security of your system. You want to keep the information confidential. So this is, again, we talked about this a lot. We have memory encryption. Our sensitive data inside the trusted execution environment is confidential from like everyone outside of the trusted execution environment. It's called confidential computing after all.
Yeah.
So integrity protection, we have multiple levels of integrity protections, right? So we talked about attestation, and we can basically verify the integrity of the system remotely. But we also talked about the secure nested paging feature of the AMD chips. Mm-hmm. So it has not only memory encrypted pages, but these are also integrity protected. They achieve this by using AES, so the advanced encryption standard, in a particular mode called Galois counter mode for all the crypto nerds out there, which is achieving both confidentiality and integrity in one go. Mm-hmm. So if someone messes with the memory pages, even if they can't read it, they try to flip a bit or something to attack your application, the processor will actually notice that someone tried to manipulate the memory page. So a lot of integrity checks going on.
I see.
Availability is an interesting one. Imagine you rent out a confidential virtual machine from Google Cloud, and let's imagine it has the property of availability. It guarantees availability to the user of the confidential virtual machine. Okay, now I'll just take back my credit card, and Google is not able to shut down the CVM. This is not going to fly. So
of course,
the hypervisor still has full control about the state of the virtual machine. Is it running? Is it stopped? Is it like destroyed? But it cannot look into the contents of the VM.
I see. Yeah. In the article, it was explicitly said that availability is pretty much sort of outside of the control of confidential computing.
Yes.
Because it is something that you typically want to have the cloud provider ensure, right? I mean, the example you mentioned of credit cards is probably an extreme example. The one I was thinking about is like, well, what if the HSM storing the keys that act as the source of truth or as the root CA are not available anymore, right?
Yeah.
Available from availability point of view, right? So how do you ensure the CVM will boot and get encrypted and decrypted the way it's supposed to?
Yeah, exactly. So I think the point in the article we tried to make was like availability is really a concern of the cloud provider. They want to have like good availability and SLAs to like get customers. So it's really like nothing that confidential computing needs to tackle. Like the cloud provider will make sure that stuff is up and running if they want to keep you as a customer.
Yeah, of course. I mean, it's in their interest, right? So, all right. So let's jump boats a little bit because this is, after all, the Kubernetes podcast, and I think a lot of people will care about. So all this stuff you've been discussing, how does it play out in the context of Kubernetes itself?
Right. There are a lot of interesting use cases, actually. So this totally depends on the scenario and like who do you trust inside your Kubernetes cluster. So we mentioned you could just use confidential virtual machines. They are available on most public cloud providers today, even like GA or like private preview. And you can just spawn your Kubernetes control plane, but also all the worker nodes inside a confidential VM instead of a classical one. And this will give you all the good properties we discussed today. You have the memory encryption part. You can verify that the correct operating system and so on was booted. And this will basically wrap your complete cluster and shield it from other folks inside the same cloud provider and inside this multi-tenant environment, but also the cloud provider itself and like attackers on the network. So you can be sure that you're inside your own context.
Yeah.
There might be other scenarios where you either you don't trust your administrator or your administrator being the admin of your Kubernetes cluster. So when you have a sensitive workload you want to deploy inside the Kubernetes cluster, the admin might not have authorization to actually see the data you want to process. So here it gets a little bit more complicated. Just moving one worker node inside a CVM is a bit problematic because you always have this kubelet running in the CVM, which basically gives the admin full code execution in your confidential virtual machine, which is the compute node.
Yes.
So you have gained basically nothing in terms of security.
Yeah, so I was about to ask as a follow-up question, because the way you mentioned CVMs in Kubernetes context is I am using Kubernetes clusters on top of a third-party platform. I use a confidential virtual machine to make sure my worker nodes and potentially even my control plane runs inside a trusted environment. And then I can ensure that the cloud provider does not have access to my environment, right?
Yes.
However, in a multi-tenant environment where you are running one cluster for multiple tenants,
Yes.
then it becomes challenging with the example you mentioned, which is the kubelet, but also, well, the virtual machines are still talking to a control plane, which is multi-tenant across all the cluster, right?
Yeah, so if you think about how our major cloud providers basically running Kubernetes as a service for you, usually they put a lot of things together to save on costs, like have a multi-tenant database or like control plane.
Yeah.
So like just wrapping that inside a confidential virtual machine context, again, this shields you from attackers outside of that context. So that's good. There's a security benefit, but it won't shield you from like everyone who's inside the same security context.
Yeah.
So if you move your Kubernetes cluster inside, everyone who's inside the Kubernetes cluster, again, it's just transparent for them. They're just shielded from the outside world, not from other workloads in the same Kubernetes cluster.
Exactly. So the example that comes to mind maybe is something like storing secrets in etcd, right? Because the database would be multi-tenant across all the tenants. So is there like anything in CVM that is trying to address this, or it's more like, because this sounds like a Kubernetes problem really, not a virtual machine problem.
Yeah. As you said, it's more a Kubernetes problem. It ties back to like the architecture that Kubernetes chose. You could try and like bring in enclaves again. As we mentioned at the beginning of the show, these are process level based isolations. If you are able to just move the etcd into its own process and isolate that from the rest of the system, again, you would gain some sort of security guarantees. So like everyone who's not running inside the process will not be able to read the memory directly, but has to interface with the etcd API.
Yeah.
Yeah. But as with security, you have to look at the use case, you have to look at the threat model, and then find a solution that works for you.
Yeah, obviously, I was just trying to get kind of like your thoughts on that specific topic. It feels like CVMs in the context of Kubernetes will play out very nicely if you are a single tenant on a single cluster and you're shielded yourself away from the platform on which you are running those virtual machines.
Yes.
But not from same tenants on the same, well, maybe tenants on the same cluster if you want to guarantee some sort of isolation at the virtual machine level, but still you have a shared control plane, which is, we'll see, I guess, how this progresses.
Exactly.
So then let's talk about this thing that has my favorite name, Coco, confidential containers. What is this?
Yes, exactly. And they actually try to address some of the concerns we mentioned just earlier. So Coco, or confidential containers, is basically an interface that provides Kubernetes with like the known pod interface. So it can basically schedule a confidential container for you in Kubernetes. Mm-hmm. But in the background, it uses all the cryptographic or like the confidential primitives we discussed today. So Coco can use like a confidential VM and just deploy your one pod in that confidential VM context, but have it scheduled by Kubernetes as it would have been like a plain old pod.
Okay, so it's a VM inside the container, essentially.
Yes.
Okay, cool. Yeah, that's pretty straightforward to understand. I think Coco is not the only project trying to do this. By this, I mean VMs inside containers.
Yeah.
Just Coco is adding the confidential aspect of it because, Kata containers or what's that AWS project?
Firecracker.
Sorry, Firecracker, yes, thank you. Yeah, it's doing the same thing. It's a virtual machine inside the container. Coco is just adding the confidentiality layer to it, essentially.
Yeah, exactly. So they are able to fall back onto this remote attestation report and bring in all the information that is available there, do additional sorts of verification, and give you this additional security guarantees, yeah.
Yeah, I could see that being a very valid use case for still using somebody else's Kubernetes cluster for jobs, where you have a job that you need to execute. It has a finite amount of time it will be running at. And basically you are exposed an API server. I mean a Kubernetes API server, you just send your job definition and then you use Coco to say, well, run my job inside the confidential computing, which is a virtual machine, and then get back my data, but also the report of where is this thing running, right?
Yeah, exactly.
Yeah.
A lot of the work the Coco folks are doing is basically figuring out which parties do you need to trust. And again, like this kubelet comes into play. It's like the Kubernetes control plane basically has full control over all the execution that is carried out in your worker nodes.
Yeah.
So they're working very hard to get a good security story for like confidential containers in a somewhat untrusted Kubernetes cluster.
Yeah. Yeah. Well, we'll see. We'll add some links to the projects. I think it'll be interesting to keep an eye on to see how that progresses. So, okay, we talked quite extensively about confidential virtual machines. I think the first thing that comes to mind as we are discussing is the overhead. I mean, this must have an overhead. Like starting a virtual machine with the fully encrypted memory, there is some additional processing that needs to be spared to do this. Is the overhead so significant that it actually makes this difficult to adopt, to justify from like a cost perspective? Or
I don't think it makes it difficult to justify. So there's definitely some sort of overhead. We don't have a lot of good real world benchmarks to actually put numbers to it. We have like some vendor benchmarks, which are like in the range of like 1 to 5%, depending on like if you're heavy disk usage or so, it might go up to like 5 or 10%. But it's like if you weigh the cost of 10% additional compute overhead to like the security gains, I think it's well worth it for most applications, and especially for applications that handle sensitive data. So we see a lot of machine learning is getting more and more popular, and you need to have the compute to like train your models. And if you want to train on stuff like medical data or like financial data and all this sensitive information, you really need to have like a trusted environment to carry out these computations.
Yeah.
And then 10% overhead, I think is fine. A good price to pay.
Yeah, again, as you said, it always depends on the context. Maybe 10% in a very high sensitive environment, it's justifiable because the benefit you get from it outweighs the cost, right? Okay, cool. Then before we close out, what are other use cases that we have for confidential computing? We've been discussing quite a lot Kubernetes itself, but like, are there any other use cases?
Yeah, definitely. And like, I'm super keen on talking to folks on like how to get confidential computing in your use case and basically take advantage of it. I have previously spoken at SIGSTORCon end of last year, where I presented an idea on how to use confidential computing to basically have verifiable build runners in the cloud. So when you think of like GitHub Actions, you want to know which runner you are using, and does the runner use a good set of like compiler toolchain and operating system? Is this all actually genuine compiler toolchain, or has someone put in the backdoor into my compiler? So if I use this feature of remote attestation, I can basically store this attestation report with my build and my final binary and so on, and like check that no one put in a backdoor in the compiler when my program was built.
Oh, interesting. Okay. Yeah. So I think that's a very interesting use case, which is basically tied to what we've been discussing, just running your code on untrusted between quotes environments and being able to have a way to cryptographically verify what's going on there.
Yes, exactly.
Right. Cool. Yeah. I mean, there's a lot of things that we have been talking about. I guess that people will have to do a lot of Googling to understand the terminologies. Before we close this out, I would like to ask you about PKI on road vehicles. What's that?
So PKI is the public key infrastructure.
Infrastructure. Yeah.
This is basically the public-private key pairs you need for like the scenarios of certificates and signing, like all the asymmetric cryptography you want to do. So like cars in the past were like not very smart, but in the future we could imagine like our cars communicating with each other or communicating with like road signs. If there's like construction work going on, like you want to warn your car there's like a construction heading your way, like a construction site, you want to slow down.
Yeah.
But you also want to make sure that this is secure, right? Like an attacker could just like send random warning notification and cause total mayhem on the streets.
Of course, yeah.
So in order to enable all of these use cases, you need identities. This is basically the foundation for every cryptographic system you want to build. Yeah, so we built a PKI, give certificates or identities to each car that is on the road. We did some tests on actually the German Autobahn to have like roads communicate with the road stop signs and construction signs and so on. Yeah, all of this is in place and getting continuously developed. And like, hopefully in future, we have like autonomous cars talking securely with each other, with like persons on the streets, with like the road signs, everything interconnected. And this is the enabling tech stack for that.
As you were talking, I thought that that's super interesting use case with like, because, most of the cars I said today are connected. And the question is, even as a car provider, how do you actually trust that the car that is trying to do an OTA, an over-the-air upgrade, is a car that you have issued, right?
Yes.
Before, you had to take your car to the garage and then they had to hook a physical machine to it and verify the signature somehow.
Yeah, exactly. Just by providing your car with an identity, the car can reach out to the manufacturer, say like, I am this type of car from this manufacturer, please give me my software update. And you can be sure that this car is actually genuine, it will receive the correct update, and so on.
Yeah.
You also have a lot of anonymity and like pseudonymity concerns. You don't want to be tracked driving around. So actually you need a lot of like short-lived certificates and like to keep the privacy of the end user and so on. So lots of exciting challenges in that space.
Yeah, that's definitely a lot of interesting things to keep an eye on. I'm very curious to see how this plays out. And I'm very curious to see how somebody would show up at DEF CON 10 years from now and show how they managed to defeat all of this. So it would be cool.
Definitely. Looking forward.
All right. Well, thank you very much, Fabian. It was fantastic talking to you.
Yeah, thanks for having me.
I guess when I reached out to you, one of the first things you said, oh yeah, I'm a long-time listener. And yeah, thanks for just like accepting to talk to us on such a short notice.
Thank you so much.
Thank you very much for joining us for the show. We've been discussing with Fabian. You can find him on LinkedIn, Twitter at Datosh18 or GitHub as Datosh. Thank you very much. Welcome back to the show, Kathleen.
Thank you. It's good to be back.
We missed you. You've been busy.
Yeah, I had a great time being in Japan for a lot of that.
Awesome.
It's been a busy time, though.
I guess by the time this episode aired, people probably would have figured out that you have conducted actually part of the 210 episodes in Japanese when you were in WasmCon.
Hopefully. I'll probably not keep that secret for very long because I am extremely excited about that. I hope you all listened to the WasmCon episode because I did an interview in Japanese and I'm very proud of it. And also Chloe Condon helped do the dub. Thank you so much to Chloe Condon for doing that.
Yeah, it was amazing.
And also big thanks to my teammate Brian Dorsey for helping with the translation, like to check that my translation was right. Because I performed that interview in Japanese and I translated it myself.
Yeah, it was awesome. I don't understand Japanese. I was just waiting for the English part. So
hopefully you liked it.
It was, being able to conduct an interview in a foreign language is not easy, right? So we'll see. Maybe I do some parts in French when we go to KubeCon Europe in Paris.
And there's also going to be some more interviews conducted in a foreign language for our KubeCon episode. Though I suppose it doesn't count as a foreign language if it's sign language.
Well, it's a language. It's a way of communicating. So
through an interpreter. Very excited about that.
Awesome.
So for all of you who made it to this point in the episode, that's a preview for you.
Yes.
But let's talk about confidential computing.
Sure.
So thank you so much, Abdel, for this interview. This is a topic that I keep hearing, of course, because security is always popular and important and great to cover. So I hear about confidential computing every now and then. Honestly, it just sounds great as a term, but I've never really looked into what it means beyond like the very surface level of like, you don't let people see into your compute, but definitely got a lot more detail on that in this conversation. There were a lot of concepts that were new to me, like the trusted execution environment, which sounds like it's more of like a process level form of the isolation, whereas what I've heard most about probably is the confidential virtual machines. And then y'all also talked about a whole bunch of other stuff like memory protected environments by Intel, and you also mentioned swap memory. So there were a lot of different technologies that you talked about. Yeah,
definitely. It's a very fascinating space due to the fact that it all boils down to like a bunch of very basic requirements. That's what we mentioned in the episode, the CIA triad, which is like the kind of like holy grail of security. But let's start with the TE. So the trusted execution environments. Those things existed for a very long time, right? So computers, PCs had these things called TPMs, which is the trusted platform modules, which is basically where your cryptographic keys are stored, right? And that's technically a form of TE, right? So it's not new per se. It's something that existed for a while. I think what's fascinating in this space is like trying to adjust those kind of capabilities into the cloud environment, right?
Yeah, and it sounds like there's a variety of solutions for those in the know. But it sounds like the confidential virtual machines are the easiest to use. So pretty much all of the cloud providers have some kind of solution there. And they're easy to use because you get into the VM, and that's the confidential part, is whatever is inside of the virtual machine is its own kind of space.
Exactly. So it's like, you can think about it as on a high level, like process isolation, but at the VM level. So even the hypervisor is not aware what's going on. So it's fully encrypted. And then you have like cryptographic way of verifying the integrity of the virtual machine itself. That's the attestation part. So it's a pretty interesting space. We work for a cloud provider. So for us, we don't really think about it that much. But I think if you are a customer and if you're operating in certain sensitive areas, I'm thinking like defense or healthcare, basically not trusting your cloud provider is quite natural, I guess, in a way, right? You're running on somebody else's hardware. So how do you make sure that whoever you're running your stuff on doesn't look into your data, right?
Yeah, always an issue that folks want to think about.
Exactly.
And this like trusted execution environments versus confidential virtual machines, the different ways that they kind of isolate your workloads, it just reminds me so much of containers, because containers can be anything from just basically a process that's running in Linux with a little bit of stuff around it to kind of isolate it, to something that's basically a virtual machine running within the machine. So it's kind of the same thing, but with a special focus on security.
Yeah, pretty much. That's one way of looking at it as well. Yeah, exactly.
Another part that you all talked about that I thought was really interesting is the TPMs versus HSMs. Also, I thought TPM at first was TPU, because I've just been having a lot of conversations about TPUs and GPUs and how they affect AI workloads, of course, because we're all talking about that kind of stuff. But no, it's not TPUs. It has nothing to do with AI, really. It's Trusted Platform Module. And hardware security modules. So one thing that I caught there that I think is like a nice tidbit is a TPM, a trusted platform module, are super commonplace. They're relatively cheap to implement, but there's only so much that they can do. They only have a few kilobytes of memory. They can only hold a few keys, and they can only do a few different types of cryptographic operations.
Yeah.
However, the hardware security module sounds intense.
Yeah.
They're really expensive. They've got like features in place to help prevent even folks from trying to steal the hardware itself.
Yeah.
So they sound very security.
Yeah, that's what they call usually anti-tampering measures. You can think about it as like, if you watch any American action movies, anti-tampering is basically having like a little bag of dye inside like an envelope of money. And if somebody tries to steal the money, it will dye all the notes, right? It's kind of the same concept.
Well, like on clothes too, like those tags that they put on clothes that have the ink in them.
Yes, exactly. It's the same concept, except like it costs more millions of dollars, I guess.
Yeah, and also involves hardware and destroying the stuff on it.
Exactly. I just remember while we were talking, when I was working in data centers, we had to install HSMs because, for reasons. Before I go there, one thing that people, I think, don't think about it too much is that they think about HSMs as just devices that store and like supply keys. They actually do more than that. They can execute the cryptographic operation inside the hardware itself, right?
Yeah, you all mentioned that in the interview.
Yeah, because of course, if you have the keys stored in the HSM, the last thing you want to do is take them out of the HSM so you can execute the operation. You want them to be, you want to execute the cryptographic information close to where the key is, right? So that's why they are usually like beefy machines with a lot of like CPU, a lot of memory, etc.
Wow, it's like a security box.
Exactly. It's a secure box, yeah. But what I was saying is that I remember when I was working in data centers, we had to like install those things, and then you hold it in your hands and you try to put it in a rack, and they're like, oh, suddenly you're reminded this is like $2 million. So like one piece of hardware.
Wow. So I had never really thought about like the security needs of our industry are so great that many people had to come together and think about all of these like tricky ways that we can ensure that things are what they say they are, and just like put all of that into a single box even.
Yeah.
So hardware security modules kind of blew my mind here.
Yeah, it's a very fascinating space.
Yeah. And speaking of making sure that things are what they say they are, another thing that you all talked about quite a bit was the PKIs for autonomous vehicles, which when we started talking about autonomous vehicles several years ago, I mean, we started talking about autonomous vehicles before that, I'm sure. But when it's really started to become a conversation in the public sphere, I feel like this was part of the conversation of we need to have vehicles that can communicate with the road and communicate with other vehicles, which would make the whole problem of self-driving cars, honestly, a lot easier. Compared to right now where they have to just like see everything around them and try to figure it out like we do as humans, which computers have other challenges with. But so that was really interesting to hear about that Fabian had worked on that kind of space.
Yeah, so that's something I have never thought about until I chatted with Fabian, because for me it sounded like, oh, so you have a car, your car talks to a remote server somewhere, or talks to another car, or talks to like a road sign, maybe, like stuff like that, right? So I never thought about the authentication and authorization part. I just thought like, oh, just an API, right? You have a key, you store the key in the car, and then by key, I mean like a JWT token or something, not like a public key. So, and I was reminded of that when, and this is probably not related to confidential computing per se, but I do have a friend who's working with a music streaming company without mentioning names, and their clients are not always like mobile and web. Sometimes they have cars as clients, right? Like you have the app of that company built into your car, like all the new cars.
Sometimes they have cars as clients.
Yeah, literally, because
it's a great soundbite right there.
Because sometimes the infotainment of the car, you know, the system that the car manufacturer builds have the client installed on it. And then you can just log in with your account and then stream. And so we were chatting about it. And I was asking this friend, like, so how do you identify who's trying to connect to your backend, right? And they were like, yeah, PKI, public-private keys. So it's stuff you never think about. But it's like, okay, yeah, sure. That sounds interesting.
Yeah. Thinking about attacks and security of autonomous vehicles is like one of the scariest sci-fi things of the modern world, in my opinion.
Oh, yes. Yes. That sounds like an action movie waiting to happen.
So I'm glad folks are working on that.
I'm also glad people are thinking like, oh, let's just have something more secure than just like random tokens and passwords.
Yeah, that's kind of important.
Exactly.
So I definitely learned a lot from this conversation. I'm glad that you all did this because I learned so many new terms that I need to go read up on now. We took a bunch of show notes, so make sure if you also want to read up on these terms like I do go check out the show notes for links to like the white paper and all sorts of other resources about stuff that Abdel and Fabian talked about.
Awesome.
Yeah. All right. We'll see you next time.
Thank you very much.
We'll do the wrap up now.
Sorry.
Welcome to us trying to wrap up this episode. We just went off in a random direction and now we're here.
Yes.
So thank you again for that interview, Abdel.
Thank you.
We'll see you all on our next episode. That brings us to the end of another episode. If you enjoyed this show, please help us spread the word and tell a friend. If you have any feedback for us, you can find us on social media at KubernetesPod or reach us by email at kubernetespodcast@google.com. You can also check out the website at kubernetespodcast.com, where you'll find transcripts and show notes and links to subscribe. Please consider rating us in your podcast player so we can help more people find and enjoy the show. Thanks for listening, and we'll see you next time.